As the world moves to lower greenhouse emissions, nuclear generation has cemented itself as a major contender for energy generation. However, there is an issue. Nuclear generation produces deadly radioactive waste. Currently, over 81% of the world's nuclear waste is stored in these spent fuel ponds. The water acts as a protective layer around the waste, absorbing 99% of the radiation emitted. These pools must be inspected on a regular basis to ensure that no issues are arising. However, the inspections are often repetitive, and as such, autonomous robotics are starting to be used in place of humans. The University of Manchester has developed one of these robots, Mallard. Capable of autonomously monitoring these ponds, it can do the work in a more accurate and safe way than any human.
Like all autonomous robots, it needs to localise itself within its environment. For Mallard, this is done via the use of a LiDAR, working with a simultaneous localisation and mapping, or SLAM algorithm. The LiDAR measures the distance to an object or wall using a laser. However, the current LiDAR on Mallard can only produce a planar scan. This causes an issue when Mallard experiences wave disturbances, as the variations in pitch and roll cause the beams to miss the walls of the pool. This loss of data can cause the robot to lose its localization capabilities. We have designed a solution to this problem, a software gimbal. A new multi-beam LiDAR has been installed onto Mallard to allow for a 3D scan to be obtained. Alongside this scan, Mallard is fitted with an inertial measurement unit that will measure the robot's orientation. The combination of these sensors allows for the implementation of the software gimbal that can correct for the roll and pitch of Mallard and produce a stabilised, planar scan. This system has been implemented as a removable, waterproof box and is designed to have minimal impact on the payload capacity. We have validated this system via extensive field trials, the results of which can be seen here. The data shown on the right shows both the old planar LiDAR scan in red and the new software gimbal scan in white. Both are trying to detect the pool wall as seen on the left. However, the planar scan starts to pick up erroneous data where the gimbal does not. Overall wall detection rates have improved from 40% to 80%.
Testing the software gimbal requires constant access to a pool, which may not always be available. In order to test Mallard's software and sensor suite in a lab environment, the University of Manchester created Mallard. Mallard is a land-based mobile robot that can move in 3 degrees of freedom: X, Y, and yaw, and is designed to accurately simulate and reproduce Mallard's motion in water. 3 degrees of freedom was not fully sufficient to test the software gimbal, and as such, a motion platform was added to enable additional movement in Z, roll, and pitch. The motion platform consists of 3 high-speed linear actuators, designed to integrate with the existing system. This enables it to move the measurement instruments freely. With this, recorded real-world movements can be replayed by the platform, allowing for testing outside of an aquatic environment. Users can also input movement via joystick controls, which are fed into a newly developed aquatic simulation software. This allows Mallard to fully simulate disturbances without the need for a pool. Both methods enable more rapid testing of software changes, which allows for validation of systems before field testing. An example of this is shown here, where the software gimbal is being validated in a lab environment.
Both Mallard and Mallard have needed work across many areas of electrical engineering, as well as significant organisational and managerial efforts. Through this work, we have also performed 2 field trials in order to validate systems and collect relevant data. To summarise, we have upgraded a platform to enable more accurate lab-based testing of Mallard systems, and also improved the robustness of the localisation method via the implementation of a software gimbal. Future goals of this project are to further increase the accuracy of the software gimbal beyond 80%, and to extend the Mallard aquatic model to include external disturbances such as waves.